And that next point is the average element size. So this is also one of the important criteria considered for checking the quality of the element, right? So from last lectures, we are going through the different criteria that are used for checking the quality of element, and this is one of that. So this criteria is average element size. What is the meaning of this average element size? Very simple meaning actually. In finite element analysis, the average element size refers to the calculated average of the characteristic lengths of all the individual elements within a mesh. So all the elements which are we are using in the meshing, if we go for the average of size of all elements, average of that all size, that we are going to call as average element size. Actually, the name also indicates what it means actually. So essentially, it is representing the typical size of single element in the model. So average, what it gives? It gives the overall view of what must be the size or what is the size differences or the average values of that parameter. So it is actually indicating that, and it is the key parameter to consider when setting up model to ensure the adequate solution in areas of high stress gradient while managing computational cost. So actually, computational cost get affected by that size. When it is smaller, computational cost is going to be more. But we need some optimum size so that can be used for getting the accurate results. So the important in meshing is it gives we have a lot less size, small size we can say, and whereas the disadvantage is it actually uh, increases the computational time and cost, like that. So when this point will be asked, you have to explain this in 2 3 statements with the key features of that. From exam point of view, I'm talking. If I go for the next point that comes in our lecture is every higher order element versus refined mesh. So this point also you consider as an important point, and many times this question is repeated that differentiate between higher order element and refined mesh. So what is the differentiation that we can do, or what are the point under which we can compare these two? What are the two? One is higher order elements, and second is refined mesh. So actually, higher order element also comes under refined mesh. If we have the P refinement, but here specially he is actually talking about H and P refinement. What is H and P refinement? For that purpose, you need to uh, go for watching the previous sessions videos, in where we have gone through the details about H refinement and P refinement both. Where in case of refined mesh, we can call that as a H refinement, whereas in case of higher order element, it can be called as P refinement. The key points of that two are here discussed. What are that? First, if I go for H refinement, it achieves higher accuracy by dividing the domain into more smaller element. So we are actually going to modify the size of element, and from bigger to smaller. If it is smaller, more number of elements will be there, which we are calling as a refined mesh. Okay, so it requires remeshing in geometry to create a final mesh. Of course, remeshing is required and may be necessary in areas where high gradients or complex geometry is there, or stress concentration is there, or a complex shape is there. In such cases, we required this particular H refinement or a refined mesh in that particular areas. What is the example? The example is dividing a beam into several smaller elements to capture stress variation near a concentrated loads, right? So we are just going to increase the number of elements in this case when we are going to refine the mesh. Whereas what that in case of higher order elements, which we are also calling as a P-refinement. So uses higher order polynomial within within each element to represent the solution more accurately. So we see in that order of elements. When it is small order, then we can go for higher order. When we go for higher order, the polynomial equation goes on increasing with a higher order variable. So when it is higher order variable, definitely it is going to be complex to solve that. So here, instead of increasing the number of elements, what we are going to do is we are going to increase the order of polynomial equation that can achieve high accuracy with a relatively coarse mesh compared to H refinement. What is the meaning of this statement? Here, higher accuracy can be achieved even though the mesh is coarse, even though the mesh is not fine, even though not increasing the number of elements. With the same elements, just increasing the number order of that level equation, we can get the higher accuracy. So third point is it may require more complex calculation due to higher order polynomial. Definitely, it requires that. What is the example? So the example is using a quadratic or cubic polynomial within a single beam element to better represent the stress distribution across the element. So what we are going to do is the element polynomial we are going to change and we are going to increase the order of that polynomial. So this is the comparison between these. These are the points related to refinement and these are the points related to higher order element. So there are some important announcements also that I want to do at the end of this session. So next going for the uh, another point which is remain, and the name of the point is actually mesh independent test. But we also call that as mesh convergence. And as you remember in the last session and last unit, first unit, this point comes what mesh convergence. And I told you that we will go through the detail of that convergence in the next unit, and therefore I am keeping that pending. So just introduction that was given in that lecture. Now here you can see that we are going to understand that mesh convergence also in detail. So let us consider a convergence of finite element model of a steel beam. For example, we are taking the steel beam. We will form the mesh of that. Okay. Stated example is a rectangular beam. So mesh parameters can be varied in three directions. When it is rectangular beam, we can rectangular means rectangular cross section. Okay, it has some length and rectangular cross section. So element size or number of divisions can be varied for that particular three directions. What are that three directions? That are beam width, beam depth, and beam span. Beam span means length of beam. So width, depth, and span are the three directions where we can increase the number of, or we can vary the number of elements or element size. So if that is done, what happens? That we'll see. Okay. So here I am showing one table. Can you see here in the table? You just understand what is this table is. Number of divisions. Here you can see FEM mesh characteristics. What are the characteristics? Here we are going to take the number of divisions of elements actually. Okay. So along the width, what will be the number of elements? Along the depth, what will be the number of elements? And along the span, what will be the number of elements? So by changing or varying this number of elements along width, depth, and span, what will be the number of element, total number of element that is here in the next row? That is the total of that. Okay, total of that means considering all cross section and length. It is not total of this. It is 14 actually. So actually we have to calculate that by calculating the how many number of elements that are formed. So here you can see that the number of elements along these columns goes on increasing. If I see for the width, can you see? In the first column, we have two elements. In the second also two elements. But in second, we increase the number of element of depth. From 2, it is 4. Right? Whereas if I go for the third column, the number of elements in the width is same. Number of elements in the depth is also same 4, but the number of elements in span are increased from 10 to 20 and so on. So we go on increasing the number of elements up to ninth column in width, depth and span all. So according to that, the total number of elements that we have are going to increase from this 40 number to 80, 160, 800 and so on. Here, can you see it is 1,22,880. For example, if you need to give in an exam, you can take this table and you can put some random values which must be increasing. Okay, it is not required to calculate or mug up these values. You can take any values, but you just take care that they must be increasing in the column wise, right? And here also in the bottom side, you can see two rows more. That is FEA result. So what is that FEA result? That FEA result is maximum deflection, and that is in inches. Mostly we use SI unit, that must be in mm, but here we have that table as a reference and where they have calculated that in inches, and that is minus 0.00066. So negative sign actually indicates the compression. Okay, it has the meaning of compression. So it, you can see that it is 0.066, then it goes on minus 1 0.135, then minus 224. So as actually this is the final result. Okay, so when number of nodes are less, we have this result. Where we increasing the number of nodes, the result is changing. If we go on increasing the number of nodes, the result is changing and it is going varying and varying again. So as you can see in the row, that as we go on increasing the number of nodes, the result go on converging. That means it is going on similar then after. Here it is variation is very high. But you can see that 272, then 270, then 277, then 275, 277, nearer results, and 278, very nearer. So if I go on increasing, this result is going to be constant then after. It is not going to change even if you are going to change the number of nodes. So in this way, that value which then after not going to change is going to be the accurate result. You have converged that result. That is called as actually converge. And this is also called as mesh independent test. So this is the testing that is done. So what is the next row that we have? That next row we have is solve time. Solve time, can you see? For the less number of nodes, we have 5 seconds required for the results to come. But as we increase the number of nodes, you can see the time go on increasing. Here it is very small variation. 5 seconds, 7 seconds, 10 seconds, 23 seconds. Here it is taking more than a minute. But what can you see here? The value of time required. For this last case, it is 3 hours, 5 minutes and 54 seconds. It is more than 3 hours are required for the same case if we are increasing the number of nodes. But we are getting the accurate result, but time is increased. Time required for that is more. So in this way, the test can be done for optimum result, compromising on time and cost. If you want, if you have less time, you can go for the less node, but the result may be inaccurate or error. And if you want accurate result, simple time it will take more, and the cost of the project therefore will increase. So this table, whatever I shown in the statistics, is also represented in the graph. Can you see here? In the first graph, I am just showing that how the result of deflection goes on changing from increase of number of nodes. So on the x-axis we have number of elements, or number of, not nodes, number of elements that are going on increasing, whereas in the y direction we have the deflection, that is result. Why that? The result in the small node case, less number node case, is here somewhere, which goes on decreasing like this, and then it is going on taking a horizontal line because it is converging here. It is nearer value. These are very nearer value. So when you will go on more number, you will find that the horizontal line will be received, that there is no change in the result, even if the number of nodes are increased. So we need to finalize the number of nodes which will give you the correct result and accurate result, and the time is also required, is not so more. Here in the second graph, both curves are shown. One that is showing the results that you can see in the blue line, whereas the green line is showing the time which goes on increasing as we go on increasing the number of element in. Okay, both curves are shown here. One is advantage and the second one is disadvantage. So you can show such graphs also if you want to explain this mesh independent test, right? So this is one point that was remained, and let us go for the next point for this particular case. So this is the last actually point that we have. Okay, so I'm going faster than the usual because I think in offline mode you have now gone through the concept of this machine, and you have understood many of the things. Now you can understand the things easily with this particular speed. And second thing, as I am recording this, therefore I'm going to upload this video also in the YouTube. Therefore, you see that here. So this is the last point that we have for the unit 2, and after that we will have conclusion of unit. At the end, we'll go through the content again, whether all the contents are covered or not according to syllabus, and we'll go for the last slide, that is course outcomes, whether that outcome is achieved or not. So welded joints and bolted joints representation in the answers that we are going to learn here, how to represent that, and you must learn this bolted and welded joint in your design subject, how to design bolted joint and how to design the welded joint. So first, if I take the welded joint representation, so here some of the basic things we need to understand, and that are static strength and fatigue strength. So what is static strength and what is fatigue strength? So that is also there in the design subject. Fatigue is related to dynamic load actually. So when I go for static strength, then the basic consideration that we need to keep in mind are static strength of weld, what weld that I'm going to use for joining two plates, suppose, which we call as parent material. So static strength of weld must be greater than or equal to static strength of the parent material. That is what are the plates that we are going to weld. So static strength must be more for weld, or otherwise how it is going to hold that. And fatigue strength of the weld must be or is very less, much less than the fatigue strength of the parent material. So it is a drawback of weld actually. So these two things when we keep in mind, we can go for representation of that. So basic fundamental that is considered for representing that welded joints are If I need to join these two plates, one you can see in yellow color, can you see? And second, you can see in the blue color, and hashing is done for that. And yellow is having T1 thickness, yeah, and blue is having T2 thickness. So we consider these plates which are going to be welded as a single plate with the thickness T1, T2 when we are going to design that, or when we are going to model that in the ANSYS, and according to that we are going to deal with that particular way. So this is the classical approach for that. And instead of this plates joint, if I have the beam element where we have to show the weld joints, and the weld is the spot weld. You must go for learning this, what is a spot weld and all. So if it is spot weld, suppose here this particular portion is to be welded with this bottom plate. You can see they are meshing, you can see here. So here you can see these points, and these points are spot welds actually. Here at this point I need to go for spot welding. But how to represent these spot welds in the ANSYS? So that spot welds are actually represented by beam elements. They are represented by beam elements, and here each spot will be one beam, and the diameter of that beam is going to be the actual spot diameter. So spot welding needs a diameter where we are going to weld that. So that spot diameter is going to be the diameter of a beam which we are going to consider as a weld joint. Getting? So then after we can go for considering that as a beam, and then after we can go for the analysis and so on. The another thing that is required for that is the beam that must be, if we are going to consider as a beam, it must be exactly perpendicular to the surfaces which we are going to weld as a spot weld. Right. So if I go for the next modeling of bolted joints, okay. So bolted joints, if you remember, you learn in design. Here I am showing one image where bolted joints are there. Can you see where that bolted joints are? Actually, this image is showing the screws. Eh? Here you can see the screw, and here also you can see the screw. And for this angle also you can see these two screws that are used. Uh, Screw or bolt that we can use. Okay, so when bolts are used here, both positions that are designed using some design concepts, and you must have designed that. I don't know whether that is there in the design of machine element or in the design of transmission system, but it is there in the syllabus. So if we need to design that, there are some parameters that is to be considered in case of design. But what if I want to use this bolted joint in the model in ANSYS, and thereafter we are going to go for the analysis of that. In such cases, what are the considerations that we are going to take in mind so that we can design that, or we can model that bolted joints in ANSYS that we are going to see now. So for modeling bolt joints, okay, minimum two layers around the bolt holes representing washer or bolt head are recommended. What is the meaning of this? So bolt, if you are going to go for bolting two plates, what you need is you need to make the hole, and the hole diameter is going to be same, or some tolerances are given for clearance fit as that of the shank diameter of the bolt. Shank means the extended portion of the bolt that is shaft type, rod type. We call that as a shank. You must know this terminology also. And head of the bolt and shank of the bolt. So shank diameter and the hole diameter must be same, or a hole diameter is somewhat greater than the shank diameter for keeping the clearance fit. So also you need to learn what are the type of fits, type of tolerances, and so on. So if the diameter of hole is something 10 mm, then the layers that we are going to consider for analysis that are recommended as to be 1.5 to 2 times of the core diameter, that is the hole diameter. If it is 10, then you consider the 15 mm or 20 mm area, diameter area for analysis, because that particular area, due to the head of the bolt, or if the washer is used in between, then that washer or bolt head is going to apply that pressure on that particular area, and therefore we need to consider that particular area for analysis. So that particular area is under certain fluid, or you can say the pressure, or you can say the uniformly distributed load, and that particular area to be measured according to that. So actually the general consideration is two times. 1.5 to 2 is given here, but 2 is considered, more is better. So 2 is considered. If it is D diameter, core diameter, then D diameter means whole diameter, then 2D will be the area we are going to consider for analysis. Okay, so 12 to 16 elements on circular hole. So we are going to consider this number of, this is actually recommended. 12 to 16 elements you have to mesh on that particular circular hole. Whereas usually the aim is to analyze parent structure, not bolts. In case of welds, we go for analysis of weld and parent material both. But here we are going for the analysis of a parent structure where bolting is going to be done. It is not the analysis of bolt, it is the analysis of the structure which you are going to bolt. So what are that particular elements that are preferred in such cases are either it is 1D or RBE2 or RBT. It is rigid body elements. So RB2 or RB3. I said that in one page we will go through some other terminology also for the elements. It is not 1D, 2D, 3D like that. They call it shell element, brick element, quadrilateral element, hexahedron element, RB, RB2, RB3, and like that. So these are the recommendation for the voltage joints. If I go for the beam element to be used as a bolt, okay. So in that case, the beam here shown like this. This area you can see actually is twice of D, the whole circle out of that. Where D is the diameter of this beam. So I can consider this beam element as a bolt, and thereafter I can go for meshing that. Here can you see that if bolting is done here, the meshing nearby to that is somewhat refined mesh. Okay, here on the bottom side also, because we have a stress concentration nearby the hole of the bolts. So in this way, the bolted joints are going to be modeled and represented, and these are the considerations that we need to keep in mind when we are going to go for analysis using bolted joints and welded joints.